Hi, my name is Brandon Graysley. I'm a high school math teacher. We're going to talk about discrete probability distributions today. So far, we've learned about probability experiments in which you have some number of trials. Each trial results in a single outcome. What if you want to analyze all of the variety of outcomes that can occur and how likely each of them is? Well, we've talked about some of those already using just basic ideas like events, where an event is a collection or a set of outcomes. What if we want to talk about things like what's the probability of a certain group of events happening? Or what if we want to know what do we expect to have happen in terms of value? So we're going to need a concept of value, which we haven't really had, excuse me, we haven't really had so far. So let's talk about this idea. It's called a random variable. And it's essentially a function that takes every outcome and assigns it a value. So a random variable x, I guess we could say a random variable x, it takes on a single value for each outcome in the sample space of a probability experiment. So one value only takes on a single value for each outcome. Now that value can repeat, that is more than one outcome might have a single value, that's going to be fine. So now we're going to add sort of one layer to this experiment trials outcome, and each outcome sort of on the side here also produces a value. So let's look at an example. This is an example we've probably already seen before. What if you're in your experiment, you roll two dice, two D6 dice. They have 6 sides, numbers 1 through 6. The sample space would look something like this. Might have 1, 1, 1 on the first die, 1 on the second die, 1, 2, and so on, all the way up to, well, we'll put some of the middle ones in, like 3, 2, 3, 3, and so on, all the way up to 6, 6 at the very end. But you can't really see that. Let me try to squeeze that on the screen for you. There we are. Now the number of different items in this sample space is 36. That's the size of the sample space. So in order to turn this from a list of outcomes into values, we might do something like the value of an outcome is the sum of the dice faces. And then in that case, the list of possible values, this is not the sample space, these are just the possible values. They are 2, 3, 4, and so on up to 12. So we can make a random variable which takes an outcome like this and converts it into a value like this. And then we can say things like we've done in the past, like what is the probability that we get a 3? Now we don't mean rolling a 3. What we mean there is that the value is a 3. And so we actually usually write it like this. Well, we'll write in one of these two ways. We'll either write x equals 3, meaning the random variable takes on the value 3, or this is the probability of getting an outcome whose value is 3, or we'll write it like this, it's a little bit shorter. So we would count how many outcomes will do that. 2 outcomes give a value of 3. If you get 1, 2, or 2, 1, out of 36 outcomes total, that's 1 in 18. Now, we already know how to do this. We've done this before, but this is a new way of describing it. So the value is the sum. These are the different values that are possible. Every outcome results in one of these values, and we can look at the probability of that value or a range of values occurring. So let's look at a different experiment. What if we flip a coin 3 times? So this is a trial. It results in an outcome. One outcome is the result of 3 flips in a row. So the sample space, we could list the whole thing, but let's not do that. The sample space looks like this. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. And so on, all the way up to tails, tails, tails. This is a size of 8. So in this case, we can have the random variable take on the value that is the number of times that, let's say, tails occurred. So we'll use a statement for this. Let x be the random variable. That takes on the value equal to the number of times tails occurs in the outcome. So the number of possible values is just a few. We can have 0 tails, 1, 2, or 3. These are the possible values. So to be really clear now, the list of outcomes is still the same. There are 8 outcomes. There are only, in this case, 4 different values that can occur. And what we'll see now is that they're not all equally likely. So let's say for the value x equals 0, this happens when this event occurs. There's just one way that that happens. When x equals 1, the event is heads, heads, tails, heads, tails, heads, or tails, heads, heads. 3 different ways to get that value. And before we might have described this and said, what's the probability of the event that we get exactly 1 tail? Now we're calling that a number. So we're oops, sorry, that was a 2. So we're counting how many different outcomes result in this value. I guess we are going to list the whole sample space eventually here. There's x equals 2. And the last part, the list of outcomes for which x equals 3, that is when there are 3 tails. They are all tails. Okay, so we can use this now to calculate our probabilities. The probability that x equals 0 is 1 out of 8. 1 outcome out of 8 outcomes in total. Each outcome is equally likely, but each value is not, or not every value is equally likely. 3/8 for 1, 3/8 for 2, and 1/8 for 3. I want you to notice these add up to, or sum to, 100%. All of the different outcomes have been represented, and so all of the probabilities are represented as well. They all add up to 100%. So this is normal. This always works this way. If you add up the probabilities of all of the possible values, you should get 100%. So this leads us to a table. The table is called a probability distribution table. Let me write that down for you. Now, these are actually pretty handy. They will show us the values, which we usually represent with a lowercase k, or sometimes an x with a subscript, but with just k when there's only one. And then they have the probability that goes with them. which is the probability that x equals k, or sometimes we'll just write p of k. So this is a table. That wasn't a very straight line. These are the four different values that we can have for this experiment. These are the probabilities of each of those values according to the stuff we just finished, and we could write that, for example, as percentages or decimals or something like that. And notice once again, they always add up to 100%. They always add up to 1. So I have a question. We call this expected value, this next part. How many tails do you expect to flip? Again, we're doing 3 flips. So if you were to run the experiment once, run one trial, how many tails would you expect to flip? Now, running a single trial, of course, you only expect to get one of these individual values, 0, 1, 2, 3. But the phrase expected value is sort of like an average, or what we would call a weighted average, of all of the different values. So let me show you what that's going to look like. What we'll do is we'll take the value itself and multiply by the probability that that value occurs. And we'll do that for each one. Maybe I'll put brackets around this to show you. Oh, I'm sorry, I wrote that backwards. Value 1 times the probability that it occurs, 3/8. To that, we're going to add the value 2 times the probability that it occurs. And last, the value 3 times the probability that it occurs. So let me just recap here. 0 times an eighth, that's the probability that it occurs. 3/8 of the time we have 1. 1 times 3/8, 2 times 3/8, and 3 times 1/8. So let me just multiply all these. 0 plus 1 times 3/8 is 3/8. 2 times 3/8 is 6/8. And then 3/8 at the end. That is, well, I already have a common denominator, so let's say that's 12/8. Or, as a decimal, you might like this, 1.5. So you expect to flip 1.5 tails on average, which is, half the time. So that's good. Now, we don't have to even have a specific situation for us to use a table like this. I'm not going to tell you what this table is. We're just going to write it out. I don't need to give you a story to go with this. We can analyze this without the story. So here are 3 values. And here are the percentage probabilities that go with them. I know this is a valid table because the probabilities add up to 100%. If they did not, or if one of them was missing, then I could fill in the missing one, or I would see the problem if they don't add up to 100%. So let's look at the expected value. It's also called the expectation, if you're interested in that. So you might see that sometimes, the expectation or expected value is, well, we have the first value 0 times 10%, and using percentages in calculators can be tricky, so I would recommend using a decimal equivalent, 0.10. 5 occurs 30% of the time. And last we have 20 occurs 60% of the time. Adding these up, we get, that's a 0. 5 times 30% is 1.5. And 20 times 60%, that's 12. So the average value for this experiment is 13.5. And we don't even know what this is really about, but if these are the real probabilities that these values occur, this is the average value that you would expect to have occur. Now we have a symbol for this, or notation. This is E of x. Capital E, capital X, and that's the random variable. I didn't label it here, but that's what we very often use. X, Y, Z, capital letters. So there's a formula. The expectation, E of x, is this. I'm going to use subscripts here. You take the first x value. Now this is like k, but because we're going to have a series of them, we don't use k. We use x like a variable, and we put subscripts there. So x1 times the probability that x1 occurs. That's multiplication right there. You can put a dot if you want to, but it's not really necessary. And then you do that for the next value. The second value times the probability that that value occurs, and so on, up to the very last value. And there are n values generally. So what this says is take every value, multiply it by its own probability of occurring, and add all those up. And we even have a special shorthand for that, which I'll just show you very briefly. And if you're in my class, we'll get into it in more detail in a little bit. It's called a sigma. Sigma is a Greek letter. It's a capital Greek letter. We put a lower bound on it. Here we say I starts at 1, and it goes up to n. 1, 2, and so on up to n. And the I is going to represent our little subscript here. X subscript I times P of X subscript I. Now if you've done any programming, you might be familiar with a for loop or other kinds of loops. These are like loop counters, so you can use that as a way to remember how it works. Okay, so let's do a few more. Let's find the expected value of this experiment. Let's see, K and P of K. I'll put 1, 3, and 5. We do tend to write these in order from lowest to like smallest to largest here. That's normal to do that. It's not necessary, I guess, but makes it a lot easier to read. Okay, so I'm going to fill in these three values. I haven't filled in the last one yet. The first one's 15%. The next one's 20%, 0.2 or 0.20 is 20%. That's 35 altogether, which means the last one has to be 65% if it's the final one. Let's calculate the expected value or expectation. That's going to be 1 times the first probability plus 3 times the second probability, and last we'll get 5 times the third probability. Not sure if you can quite see that. There we go. Let's see. That will be 0.15. 3 times 20 is 60, so 0.60. And last we have 5 times 65, so that would be 3.25, I think. Let's see, 5 times 60 would be 3 here, so 5 times 20, yeah, 3.25. And adding those up, looks like I get exactly 4, 4.00 or 4. So the expected value for this experiment is 4, which is pretty close to 5, and that sort of makes sense to me because most of the time we're getting a large value here. Most of the time, almost 2/3 of the time, we're getting the value 5. Okay, let's do another one. This one's going to use maybe a bit stranger numbers, or what will seem stranger. And this one is going to have a real context, which I'll explain afterwards. So the first value is -2. Yep, you can have negative values. Second one's 48. And the last one is 998. So you can have negative values, you can have decimal values, whole values, fractions, anything like that is fine. Now the probability of -2 occurring in this experiment is very high, 995 out of 1,000, or we could write that as 0.995, 99.5%. The probability of 48 occurring is 4 out of 1,000, 0.004, that's 0.4%, not 4%. And the probability of 998 occurring is, well, it has to add up. So this is 1 out of 1,000. That adds up to 1,000 out of 1,000. Okay, so we have our table all filled in now. All the three values, all of the probabilities, they add up to 100%. So we're ready to calculate the expected value. So using our formula, the expected value is the value times the probability that it occurs for each one. I'm going to put this one in brackets since it's a negative number. And maybe I'll just use brackets for everything. That shows multiplication. 48 times 0.004. And the last one is 998 times 0.001. Okay. Well, if you type all that in, use a good calculator, you'll get this number, negative 0.8. And you know what, I'm going to put a 0 on the end of that for a good reason in a minute, because this situation is actually what would happen with a certain kind of lottery or raffle. So I'm going to tell you the story of this distribution now. So 1,000 tickets are sold for $2 each. Four runner-up prizes, that is not the winning grand prize, of $50 each are won. And last, one grand prize of $1,000 is won. So this is the lottery. Now let's see how this relates to our probability situation. Winning tickets have value 48 or 998. A winning ticket would earn the person holding it $1,000, but they did already pay $2 to get the ticket. So the value is either going to be $48 or $998. The losing ticket has a value of negative $2. You paid for the ticket, you get nothing back, so it cost $2. You know, you earn 0, and so it's the value of that ticket was actually negative 2. It cost you to get the worthless ticket. So this is where our table comes from. Negative 2, not 0 for a losing ticket. 48, not 50 for a ticket that's a runner-up. And 998, not 1,000 for the grand prize winning ticket. Now you could instead have a different table, a very similar one. Different random variable because the value is calculated differently. Maybe this is x, and this one is y. And these values could be 0, 50, and 1,000. And the same probabilities would occur. Now your expected value then is going to be slightly higher, but you would have to sort of subtract from that the fact that you had to pay in to get these tickets. So each of these had 2 added to it, so you can imagine what will happen here to the expected value. In fact, why don't you try that out, because it's not super complicated, and you'll see how it works out. Okay, so we have a bunch of terms now. We've got expected value, which relies on the values for the experiment, all the different values, and the corresponding probabilities. So this is helpful to us in lots of ways. One is that we can do things like this, calculate the average or expected value. We can also use it, like we did a minute ago, to count things to see how likely they are to occur, like we did here with the dice. How many tails do you expect to flip? So these are sort of small examples, but we're going to look at categories of distributions like this that we can expand to use for a variety of different situations. And Once we learn a few different distributions, we're going to learn about 4 of them in the course that I'm teaching, you'll be able to handle lots and lots of probability distribution situations. Okay, so I hope that's a good start, and I will talk to you soon. Thanks.